Hello and welcome to the second video in our video tutorial series for our hydrostatics problem set. So in this and following videos, I'm not going to explicitly solve the problem, but I'm going to work through it and kind of guide you on how you go about solving these problems yourself. So here we have question 4 from problem sheet 1. We have a conduit here. If we read the question, we can see that the conduit has two square gates which close two openings in the conduit, which is connected to an open tank of water as shown in figure 4. When the water depth, h, here, reaches 5 meters, so the height here is increasing. When it reaches 5 meters, it is desired that both gates open at the same time. So if h is less than 5 meters, the gate doesn't have enough pressure to be opened up. So determine the weight of the homogeneous horizontal gate, this guy here. How heavy is he to overcome the pressure he's feeling and to keep the door closed until 5 meters, and the horizontal force or acting on the vertical gate that is required to keep the gate closed. So how much force do we have to keep this, apply to this guy to keep him closed? We have hinges. We have indicated hinges here, one hinge here, another hinge there. So we're told that the weight of the vertical gate can be ignored and friction with the hinges can be ignored as well. So just tackling this problem as we would tackle any of our other hydrostatics problems, we'll start by looking at our regions of constant pressure across this system. So here we have our free surface. So this free surface here is at atmospheric pressure. We can work down gauge pressures. Pressure here is 0 and it increases with depth. At some location here, we also have a line of constant pressure which goes from the base of the gate, horizontal gate, all the way across here, which is h minus 3 meters. So we know that by looking at this depth here is going to be h minus 3 meters, and if h is 5, then that's just 2 meters. Okay. We know that the pressure increases with depth. So the pressure here at the bottom surface is large, it's getting smaller with height. With the pressure distribution, we can use a pressure prism if we so choose. Okay. So in order to get the pressure acting here on this surface, we need to work down and back up again, all the way across to here. So we work all the way down to here and all the way back up to there. So we say that rho g h, so we're working positive down h, so h is 5, minus rho g 3, so back up 3 meters, is equal to ph, where ph is our horizontal gate. I'll just put him down there. Okay. So once you have that, you now have the pressure at h. It turns out, of course, that that is equal to rho g h minus 3 is equal to rho g, where h is 2, h is 5, so we're left with rho g2. So that's going to give us the pressure force acting here on this lower surface. We know the area is 4 by 4 meters. So pressure is force over area. Pressure times area is equal to force. That's going to be the weight of this guy acting there when it's perfectly in balance, and as soon as it tips it ever so slightly, it will lift it up. If h is less than 4 meters, the gate is too heavy. If h is more than 4 meters, the pressure will open the gate. So that's the first part solved, and you can work through the numbers yourselves. Now the second part is a little bit more complicated because our gate exists at some pressure here, some lower pressure. So there's some finite pressure just up here that we have to account for. And we know he must increase with depth down to here. So we're kind of dealing with a pressure prism again. It's like the example in the lecture notes that we had of a door that partially down, submerged, and an inclined wall perhaps. And an important thing to notice is that this region here, this area here of this partial pressure prism is equivalent to this area here, or the volume perhaps, if you want to think of it that way, because obviously it has a 4 meter depth out of the screen. So they're the same, which is convenient. We can use that if we so choose and solve this using the pressure prism, or we can go back and look at our lecture notes where we can use our where we can use what we've learned about our moments of inertia. So if we take this line here and extend it across here, we can extend this angle up here like this. Or we can work over on this side, it doesn't really matter. It's all the same. So our equation we would have developed in the lectures, we would have derived an equation for YR, which is the location at which FR is acting on that surface, and we say that YR is equal to IXC all divided by YC times the area of the gate plus YC. Okay. What is IXC? It's our moment of inertia. We can get that from the lecture notes. Here we have a rectangle, which is B times A. In our case, it's a square, which is 4 by 4. So we have IXC is equal to 1 over 12, 4 to the power of 4. Okay, that's not a very good 4. There you go. Okay, we can push that away. So with that in hand, we know that YC is the centroid location, so it's going to be the midpoint here. This is getting a little bit messy, so I'm just going to do some cleaning up. So YC is the midpoint here. We know this height of this gate is 2 meters. We know H is 5. So YC is equal to 5 plus 2. Half the gate height is equal to 7 meters. Okay, we know that the area is equal to 4 by 4 meters. And that should be everything we need to figure this out.